Well, we have two definitions, a definition and an alternative definition of the derivative. Let's demonstrate how they are equivalent to each other. So here is the first definition, and of course, the derivative at x naught is equal to this if and only if the limit exists. So let's use a small change of variables. Let's let h equal x minus x naught. And it should be easy to see why we're choosing that. In the second, or the alternative definition, we needed h to go to 0. Where in this case, what's happening when x gets close to x naught? Well, the denominator is going to 0. Okay, so if h is equal to that, let's notice what we get from that. Notice that x goes to x naught is essentially equivalent. It goes that happens if and only if h goes to 0, because h is equal to h minus or x minus x naught. So the only way to get h to 0 is have these approach each other. And how could we write x? X from this equation would be h plus x naught. I'll write it like x naught plus h. That's just using that line right there. So if we start off with this, the limit as x goes to x naught of f of x minus f of x naught over x minus x naught, that's equivalent to saying I want, instead of x going to x naught, I'm going to say the limit as h goes to 0 of f of x plus, let's see, it'd be x naught plus h minus f of x naught all over h. And all I did was substitution to get from this to that.